So we'll look at some algorithms for solving discrete logs today. And we're going to put the discrete log problem in a slightly more general setting than what we looked at last time. And so remember that we've got this notion of a structure called a group. Okay, we talked a little bit about group axioms in one of the first few classes, but just a reminder. So it's a set with this associated binary operation where you've got identity and inverses. Okay. Remember that the order of an element in a group is the least positive integer n, such that alpha to the n gives you the identity. So here's some terminology we haven't seen yet then. So a subgroup H of a group G is just a subset of G that is also a group under the same operation. And if alpha has order n, then we can look at what's called the subgroup generated by alpha. And that's just the set of all integer powers of alpha. But if it has order n, then I can get all those integer powers by letting I run from 0 to n minus 1. Right? Because alpha to the 0 would be the identity. By the time I get out to alpha to the n, I would be back to the identity, and then I would just be cycling through all those elements again. Okay, could be that an element alpha generates an entire group G, but maybe it just generates some proper subgroup of G. Okay, so the discrete log problem in a group then is, so given a group G, element alpha, finite order, and a beta in the subgroup generated by alpha, determine the unique A between 0 and n minus 1 such that alpha to the A is beta. Okay, so again, it's really just finding a logarithm again. It's finding what exponent of alpha gives you beta. Okay. Now, typically in this class, the discrete log problems that we will be trying to solve will be in Z mod n star for some end. But when we're describing some of these algorithms, it's going to be a lot easier notationally just to describe what's going on in a generic group, so that I don't have to keep worrying about this mod notation all the time. Okay. All right, so here are a few algorithms for computing discrete logs. So for example, if I want to find log base beta of alpha in the group G, I could just calculate all the powers of alpha up until n until I encounter beta. Okay, so that's sort of a brute force approach, sort of analogous to trial division. If we're working in a very large group, which we would be if we actually implemented Al-Gamal, then this is not going to be very efficient at all. Okay. Another option would be to pre-compute all the powers of alpha and then sort the sets with respect to the second components. Or maybe hash on the second component would be another option. And then so use binary search or use some sort of hash lookup to find beta. So this will be more efficient if we need to compute many discrete logs for the same value of alpha. But again, if n is very large, this may be completely impractical, right? Because maybe you've got just way too many values for powers of alpha to even store on a machine. All right, so let's look at a better algorithm. Okay, so this is what's known as Shanks algorithm, also known as baby step, giant step for solving a discrete log problem. And so the idea then is I'm going to be given alpha and beta, where the order of alpha is going to be n. Okay, and I'm going to know that beta is in the subgroup generated by alpha. Okay, so I want to find this exponent e. Such that beta is going to be alpha to the e. So what I'm going to do is I'm going to let m be the ceiling of square root of n, and I'm going to form two lists. And so I'm going to form this list L1, which essentially says, look at powers of alpha, but go in steps of m, instead of going by steps of 1. Right, so this will be things of the form j comma alpha to the mj. So where m was that ceiling of square root of n. Okay, so look at all powers of alpha and steps of n. And then in my list L2, what I'm going to do is I'm going to look at beta times alpha to the minus I, alpha to the minus I. So basically I'm going to backtrack from beta going by steps of powers of alpha that go in steps of 1. And then the idea is I'm just going to look for a collision in those two lists. Okay, so this is this first list here. So this is sort of the giant step portion of the algorithm. So look at all powers of alpha and steps of n. And then this is the baby step. So this is the sort of backtracking in steps of 1. And the idea is then eventually I'm going to have to find a value where those second entry in those two lists coincide, and then I can use those to backtrack. Okay. All right, so how do I know that? Well, by definition of the discrete log problem, this exponent I'm looking for, e, is going to be between 0 and n minus 1 inclusive. Okay. But n is going to be less than or equal to m squared, right? Because m is the ceiling of square root of n. So that means that if I look at m, it's at least square root of m. Okay, so m is greater than or equal to square root of n, which tells me that m squared is greater than or equal to n. Okay. But then this I can split up as m squared minus m plus m minus 1. Okay. And I can factor this as m times m minus 1 plus m minus 1. Okay, so if I divide e by m, then I use the division principle here to get a quotient and remainder. Then that means that the quotient and remainder are each going to be strictly less than m, right? Well, the remainder is going to be less than m because when I divide with, the remainder will always be less than the dividend. But then this is telling me that the quotient I get will be strictly less than m. All right, but L1, right, contains all powers of alpha and steps of m, and L2 contains all things of the form beta times alpha to the minus a power going from 0 up to m minus 1. Okay, so that means that if I write, so e is log of beta will be, so that'll be mq plus r, with r and q each in the range from 0 to m minus 1. So that means I can write beta as alpha to the mq plus r, okay, which is alpha to the mq times alpha to the r. Okay, so I can rewrite that equation as beta times alpha to the minus r times alpha to the mq. Okay. So this equation then is telling me there's going to have to be some coincidence, right? So this is corresponding to, right, the second entry of that ordered pair in L1. This is corresponding to the second entry of that ordered pair in L2. And so this is telling me there's going to have to be some point at which they coincide. Okay. All right, so I look for that collision in that second element. Okay. So see where they coincide, and when I find that collision, then I can reconstruct the log of beta, right? Because then this is telling me, well, so this gets me back to this equation. That's telling me that the log then is just going to be mj plus I, right? Where j is the first index of the collision in L1, and I is the first collision of the index in L2. GB Z mod 29 star. I'm going to let alpha be 2 and beta is equal to 23. Okay, so we want to find log base 2 of 23 and Z mod 29 star. So it turns out alpha is primitive in this group. Okay, so the order of alpha is 23. Oh, sorry. Order of alpha is 28. Okay, so m, right, is square root of 28 rounded up. Okay. All right, well, 28 is between 5 squared and 6 squared. Okay, so square root of 28 is 5 point something. Okay, so rounded up, it's going to be 6. And then I can generate these two lengths, right? So to generate L1, okay, so remember that is, so well, a typical element of L1 is going to be I, right, alpha to the mi. Okay, so for example, I would get 0 comma alpha to the 0, which is just 0, 1, which is this. I would get 1 comma alpha to, so m times 1. Okay, so what's alpha to the 6 here in this group? Well, that's 2 to the 6 mod 29. 2 to the 6 is 64. 64 mod 29 is 6. Okay, so that's where this is coming from. So we get 2 times alpha to the 6 times 2. Okay, so we're going in steps of alpha to the m. Okay, that's just this squared. Okay, so that's 2 comma 36. Okay, but we're working mod 29, so that's 2 comma 7. Okay, so that's where this comes from. And then hopefully you can fill in the rest of those entries based on that. And then for L2, so what are those entries? Okay, so this would be, so those are the form J beta times alpha to the minus J. Okay, so the first entry would just be 0 times beta, right? Well, times alpha to the 0, but that's just 1. Okay, so 0, 23. And then the second entry would be 1, 23 times alpha to the negative 1. Okay. What's the inverse of alpha? Mod 29, it's 15, so it'd be 23 times 15. Okay, and then I'll let you plug it in to verify that that gives you 26. Okay, et cetera, et cetera, et cetera. All right, so that's how we generate these two lists. But now the key is we're looking for a collision in the list in that second component. Okay, so I am looking for something where the first component is equal to the second, or the second component in the first list is equal to the second component of element in the second list. Okay, so notice that happens at 3 comma 13, 2 comma 13. So what does that tell me? Okay, well that tells me that alpha to the 3 times n is equal to beta times alpha to the negative 2. Okay, but m was just 6, remember. So alpha to the 18 is beta times alpha to the negative 2, and so beta is alpha to the 20. Okay, so log base alpha, beta then was just equal to 20. All right, so again, I think it looks kind of abstract in the description, but it's really not so bad when you put it into practice. Right, because you kind of go in these big steps, backtrack, and see when one of your small steps takes you to one of the powers of alpha that was a multiple of n, match those two things up, right? And then you'll be able to solve for that log. So the tricky part here will be finding that collision. So there's a couple of things you could do. You could either sort both lists on the second element, and then just kind of do a simultaneous pass through the two lists, looking to see where you find a collision. Or another thing you may want to do is hash on those second elements, and then look and see when you had two of those bins were each occupied, one by an element from L1 one byte element from L2. Okay. All right, so let's do one more example. And so we're going to find log base 2 of 13 in Z mod 17 star. We're going to use Shanks' algorithm. Okay. So the wrinkle here is, remember, we are always interested in the size of the subgroup that we're working in. Okay, so first thing we need to do here is find the order of 2 in Z mod 17 star. Okay. Well, I can just write things out, right? So I get 2, 4, 8, 16, but 16 is -1, right? Working mod 17, so if I multiply by another 2, I would get, I'll just write it as -2, -4, -8, okay, but then -16, which is the same as 1, okay. All right, so 2 to the 8 is congruent to 1. That's the first positive power that gets me to 1. Okay, so the order of 2 is equal to 8. Okay, so my m here is going to be the ceiling of the square root of 8. So square root of 8 is 2 point something, so that's going to be 3. Okay, so on my first list, I'm going to go in steps of 3, or steps of powers of 3. Okay, so for L1, alpha to the 0 is 1. Okay, but then I'm going to get 1, all right, alpha to the 1. And then I'm going to get 2 alpha, sorry, not alpha to the 1, rather 1 alpha to the m. Cubed, and then I'm going to get 2 alpha to the 2 times 3, or alpha to the 6. Okay, well, we have those already, right? So what was alpha to the 3? It was 8. So I'm going to get 1 comma 8. Okay, and then 2 times alpha to the 6. Okay, so what was alpha to the 6? So 4, 5, 6, -4, aka 13. What about my L2? Okay, so again, it's just going to have 3 elements since m is equal to 3. All right, and so it's going to be 0 comma beta. And then it's going to be 0 comma beta times alpha inverse. Sorry, 1 comma beta times alpha inverse. And then 2 comma beta times alpha to the -2. But that's 0 comma 13. Okay, and these I'm actually, I'll write out what they are, right? So Z mod 17, 2 inverse is going to be 9. Right? Since 2 times 9 is 18. But I'm not actually going to reduce those. Because I can already see what my collision is. All right, so where? All right, so I'm starting to lose my XP pen faculties here, so I guess it's a good thing we're getting near the end of this video. Okay, but notice I got a 13 in the second component there and there. Okay, so that, I mean, that kind of already tells me what log-based alpha beta is. But but just to write it out, so my equation is that, so alpha to the 2m, right, is equal to beta, right, times alpha to the 0. Okay, but again, m is 3, so that's just telling me alpha to the 6 is beta in this group. So log base alpha and beta is just equal to 6. Okay. All right, so that's Shanks' algorithm. Notice that unlike most of the algorithms we've been looking at recently, it's completely deterministic. So it's guaranteed to find the discrete log as long as you have enough time and space to run it. The problem is it's not very efficient, right? Because what do you have to do to run Shanks? Well, you need to generate these lists, which are on the order of square root of m, where m is the order of the element in the group. Okay, so if m is large, suppose we were working with a 1,000 bit prime. Okay, so m is about 300 decimal digits. So m is about 10 to the 300. So square root of m could be about 10 to the 150 in a realistic size problem. Okay, so you're not really going to generate and sort or hash lists with 10 to the 150 elements. So essentially, then I sort of think of Shanks as intelligent brute force, right? It's a much more clever way of going about the problem than just checking alpha to every power. And if your m, if the size of your group is relatively small, then it may work pretty well. But if you're dealing with an elegant model size modulus, it's not going to help you at all. Discrete log problem is still going to be completely intractable. So what we're going to do then is again look at some randomized algorithms for solving discrete log problems, and we'll look at the Pollard row algorithm for solving discrete logs next time.